Good evening, everyone.
Good evening, sir.
Good evening, sir.
The first session is module 1, the second one is module 2. Tomorrow we will do the 2022 past paper. All of it. One second. Hello? Right, my laptop was freezing up. All right, so ready again. Okay, so if we're testing on food item for the different nutrients, right? My inference is that protein is present. What would have been my observation?
The food item turned purple.
All right.
Or lilac.
If you want to put purple or
Here we can say violet too.
yeah. So typically it's purple. We use purple or violet. Color is seen. What would have been my test?
You add Bayer solution.
All right, so we use Biret. All right.
Biret reagent.
All right. So we could say we pour 1 cm cube. We're assuming that we made a mixture out of it. All right. So pour 1 cm cube of mixture. Or instead of doing that, we would need a mixture. So let me put it back. Right, pour 1 cm cube of the mixture. That's the unknown food, by the way. All right, into a test tube. And then what would we add to the test tube now?
The Biret solution.
Right, undo that. Don't remember if it's BIU or BUI for the Biret in terms of the spelling. They add 1 ml of the Biret solution to the mixture. If you don't have any Biret solution, which 2 chemicals we can use?
Sodium hydroxide and copper sulfate.
That is correct. What is the key component of the Biret reagent?
The copper 2 plus iron.
Copper 2 plus iron.
Right, that is correct. So that would be it for the Biret test. Non-reducing sugar is absent. What would be my observation?
It remained the same.
Which is?
It blew.
Right. Right, just tell me the reagents that you need to test for non-reducing sugar.
Hydrochloric acid.
Right.
Sodium,
Sodium hydroxide and the Benedict.
So we're going to boil the mixture in acid. After you boil it in acid, what comes next?
You neutralize it with the base.
So we're going to add a base. So you pick any base. It doesn't matter if it's sodium carbonate, sodium hydroxide. So you're going to add base. Example, typically it's sodium carbonate. It doesn't matter which base. We add a base. So you boil it in the acid. So you add the acid and the mixture to a test tube and you boil it. Then you remove it, allow it to cool. Then you add the base. So it's acid, then base. Then what after the base?
Benedict.
Which reagent?
Benedict
Right.
solution.
Then you add the Benedict solution. Let us say reducing sugar, sorry. If non-reducing sugar was present, what would have been your observation?
It changed from blue to yellow to orange to red.
All right. So if it was not present, it would stay blue, but if it was present,
it would be red, brick red.
so we can get a series of color change. So if present,
So it depends on how strong
right,
the protein, the non-reducing sugar is in it, I get different colors.
yeah, depending on the concentration, it might stop at yellow, green, it go to brick red. So I'm just going to put all the potential colors. So as I said, it could go from blue to green, yellow. So these are all the potential or the possible colors. Orange, then brick red. What am I testing for?
Starch.
Starch.
All right. If starch is present, all right, so let us say, or tell me, if starch is present, what should be my color change?
Blue black.
Blue black. From yeah.
And what would be my inference?
Starch is present.
Okay. No, you can get a table like this to fill in any portion without inference method or test. All right, so we test for 3. Which one we haven't tested for as yet?
Lipid.
Lipid and which other one?
Reducing sugar.
Reducing
Right.
sugar.
So the reagent for lipids, what would be the reagent if I was testing for lipids? Which 2 reagent I need?
You need ethanol and water.
If it is present, what would be my observation?
Milky white.
Cloudy
Cloudy
white.
white.
Yeah.
Cloudy white
Say-
emulsion.
I want to say milky or cloudy.
White layer.
So you ever see some droplets too? I don't know. I think so.
Right, so a milky white, so cloudy white or milky white with lipid droplets, or you can just say, once you mention the word emulsion, it would cover, so you could say cloudy white or milky white emulsion. Right. So whichever of those 2 observations that you want to use. And the inference is that lipid would be present. And of course, for the reducing sugar test, we would not need any acid or base. So if I was testing for reducing sugar, all I need is the Benedict solution. And if it is present, the color change will be the same. So in terms of observation, the color change is the same for reducing sugar as non-reducing sugar. Right? Bearing in mind that you use the acid and the base for the non-reducing sugar. All right, so that's it for the food test. We're going to move on. All right, so apart from the food test, we also do semi-quantitative tests. So in this one, we are determining the amount of sugar that is present. So you would do the Benedict solution on your samples as well as the glucose standards. So for example, let us say the 0.5% glucose, it gave you, let's say, a green color. 1% gave you the yellow-green or green-yellow. I don't know. So this is yellow, orange, and brick red. And for the samples now, let's say the lime juice, it has a yellow-green color. The orange juice, brick red, yeah, it's an orange. Or something close to orange red. This is brick red. And water is blue. All right, so based on this, right, what would you estimate the glucose concentration to be in the lime juice?
1.0%.
Just a second.
Well,
So we want to estimate the amount of glucose in each of these samples. So down here, we have our standard solutions of glucose. So remember, standard solutions means we know the exact concentration. We are using color changes between the standard and the sample to estimate the amount of glucose that is present in the sample. So, right, going again now, based on the color changes, what would you estimate the concentration of lime juice to be, the concentration of glucose in the lime juice?
So you would say between the 0.5 and the 1, since we never get an exact color.
All right, so it would be between 0.5 to 1%. What would it be for orange juice?
5 to 10%.
Right? 5, 10%. What would it be for pineapple soda?
10%.
10% glucose.
10%. And for water, it would be?
0.
0.
That is correct. So this is a semi-quantitative test. It is semi because we do not know the exact concentration. So we are using color changes and matching them up to the standard solutions. So make a comparison and we estimate it. If an experiment was to come, it can be on the food test, it could be this. All right. And so moving on again. All right, this is potato strip. So based on this, what experiment am I doing?
Osmosis.
Osmosis, sir.
All right. And so for observation, for container A, let us say the potato strip. Which of these solutions, based on my observations, all right, when you're doing osmosis, there are 3 types of solutions. Do you know the name of them?
You have hypertonic, isotonic, and hypotonic.
All right, so we have hypertonic, hypotonic, and isotonic. What happens to a plant cell in a for the hypertonic? So the prefix hyper, what does hyper mean? One means high, one means low. Hypertension, hyperactive.
So hyper mean a low water potential, a high water potential.
Yeah.
Don't go to water potential.
It's
In
high.
terms of, yeah, it means high. All right. Hyper means
Low.
low. All right. Iso is the same.
Same.
When we're using hypertonic, hypotonic, it is referring to not the water now, but the amount of solute in the water. A hypertonic solution means you have a lot of solute particles in the water. All right, so hyper, it is a concentrated solution. So hypo means that if it's hyper, only a few particles are in solution. So you have a lot of water with the hypo. A lot of water compared to the particles. So this would be hypo, this would be hypertonic. No, someone mentioned water potential. So the hypertonic solution, the hypotonic solution. Before we go to water potential, what will happen to a cell in a hypertonic solution?
It will become flaccid.
All right. What will happen to a cell in a hypotonic
It
solution?
will become turgid.
All right.
And swell.
So why will it become turgid?
Sir, because the water move from the container into the cell.
That is correct. And in the hypertonic one, water moves from where to where?
From the cell into the container.
Solution.
All right. So if isotonic means that with the isotonic, the concentration outside and inside the cell is the same. So will anything change in terms of? All right. So look at our 4 containers. If I say that container A, the potato strip increase in length and mass, would that solution be hypertonic or hypotonic?
Hypo.
Hypo.
Hypo. How you know it's hypo?
Because sir, it increased in length and mass, so that means it becomes turgid.
Which means what? In terms of the movement
So
of
the water
move from the container
right
into the cell.
What happened in container B? Why did we not see a change?
It's
Because it's
isotonic.
Isotonic.
The
Therefore,
concentration.
Therefore, the concentration in the
Concentration.
container and
Both
in the
is
cell
the
are the
same.
same.
and in terms of the movement of water,
No movement.
No
Or
water
no-
move.
right? So there's no greater net movement of water in any direction. All right. And then now for C and D,
Hypertonic.
both of them are hypertonic. Good. Now, water potential. Define osmosis for me in terms of water potential.
Osmosis is the
Is the
movement
movement
of
of
water
water.
molecules from a higher concentration to a lower concentration.
In terms of, do it in terms of.
water potential to a lower water potential.
Oh, okay.
Yeah. So let me just clear some of the board. So for CAPE, we generally define osmosis in terms of water potential. So as I said, osmosis is the movement from a region of higher water potential to lower water potential. Is that the end of the definition?
No, sir. It's across a semi-permeable membrane.
Right.
All right.
From region of higher water potential to lower water potential through a semi-permeable membrane. All right. All right, let me erase the containers. What I want you to do now, tell me in terms of container A, B, C, and D, in terms of water potential, tell me which container has the highest water potential and which one has the lowest.
That is one A.
E.
What? C is highest and A are lowest.
All right.
Would that be the highest?
A no, would have been the highest.
Yeah, A would be the highest.
All right. Before we decide on whether it's A, B, C, or D, between the hypertonic solution and the hypotonic solution, which one has a higher water potential?
Hypertonic.
Hyper.
All right, no, that is where you're making the mistake.
Sir, hypotonic.
From higher water potential to lower, so the one with the highest would be A because the water moved from the solution into the potato strip.
Yeah, but correct. But to correct the person that said hypertonic is concentrated. Now, in terms of water potential, the highest, we take the highest water potential as 0. So pure water has a water potential of 0. So pure water here means that nothing is present in it. It's just H2O. If it has a water potential of 0, once you start adding something to the water, its water potential is going to decrease. All right. So the higher the water potential, the water will move from where it is higher. So any container where water is moving from it, it would have a higher water potential than the cell. From A, B, C, and D, which one of them did water move from into the cell? Where did
A.
water move?
So,
A.
A.
Right.
I mean, container A.
Right. So container A would have the ice, right?
Yes, sir.
And then which container after that?
B.
B.
Right. So in this example, right, A, B, we are not sure between C and D. Well, once you're looking at the concentration, right, 5%, 10%, once you increase the concentration, what happens to the water potential?
It decrease. Sorry, it
Right.
decrease.
That is correct. So it's an inverse relationship. So as concentration increases, what happens to water potential?
It decreases.
Right. So water moving from a higher water potential to a lower water potential is the same thing as water moving from where it is higher in concentration to where it is lower. All right. All right, so let's go again. This molecule on the board, what is it called? Anybody?
Fatty acid.
Fatty acid.
All right, it is a fatty acid. What is wrong with this structure? And this structure here, what is incorrect about it?
It needs another OH group.
Needs another OH group. Tell us why.
Because if we are forming a phospholipid, or we're trying to form a triglyceride,
Right?
it takes three fatty acid chain for the triglyceride, and it takes a phosphate group to form the ester linkage between the glycerol molecule and the fatty acid.
I just mentioned a word there, glycerol. So with glycerol, how many OH group it have?
3.
Right. So you're correct. I was drawing glycerol, so it must have 3 OH groups. So this molecule is glycerol. And they just answered a lot of questions. So this is a fatty acid. This is glycerol. If I should combine fatty acid and glycerol, what will I form? Or what am I trying to form?
A triglyceride.
All right. So to form a triglyceride, so a triglyceride is formed from one molecule of and 3 fatty acids. Question, when you eat fatty acids, right? Not fatty acid, you triglyceride. What is it digested? and broken down into.
The fatty acid and the glycerol.
That is correct. The monomers is glycerol and fatty acid. We combine them to get the triglyceride. What is the general name for this type of reaction?
Which one? When it got to fatty acid and glycerol?
Yeah, no, when you combine glycerol and the fatty
Condensation.
and why? What is the key feature about a condensation reaction?
You produce
Water.
water. Or yeah.
Right. So you join up two compounds by removing a molecule of water. And we're going to do
You can
this.
call it esterification too.
Yes, it is also esterification. So the specific reaction is esterification. But in terms of a general or a class of reaction, once you join up two compounds and remove a molecule of water, it's condensation. All right, so let us just quickly relook at how we actually form the triglyceride. Now, when you're doing this, if you want to be very specific with the chemical structure, that is okay. All right, ready again. You can be very technical and write the 3 carbons, right? All of the H's. Don't have to. All right, so this is glycerol. But these 3 carbons, you can just draw this vertical box here. That takes care of the 3 carbons and the hydrogens. So all you need to show is the OH groups, because they are what is important for the reaction that we're going to do. Remember now, all you need to do, remove a hydrogen from glycerol and the OH. All right. As was said earlier, we are using 3 fatty acids. So you will do this for the 3 of them. Just take off the OH from the fatty acid and the H from the alcohol, from the OH group. It doesn't matter how much of these that you draw. All right? So if the question asks you to show the formation of a triglyceride, you will have to do this. All right, so if it asks you to show the formation, you will have to show the triglyceride reacting with the glycerol. All right, some areas down here. So what will happen now? If you take off the OH, by circling the OH, it means that I'm taking off the OH from the acid and the hydrogen from the alcohol. So all you will do in the new structure down here is draw a line connecting this carbon with this oxygen. So when you circle the OH, it means that you are taking off the OH and the hydrogen. Then you connect the carbon to the oxygen. All right, so that is what I will do. All right, so I'm going to draw back my 3 fatty acids. All right. Remember now the OH has been removed. And I am going to connect it to the oxygen of the glycerol molecule. On the exam, if you are using the box, just label it glycerol. Right? Then no. So these are your 3 fatty acids. I will do phospholipids after this. So 3 fatty acids and glycerol is what gives you your triglyceride. All right, so let me repeat this. If they ask you to show the formation, they want to see the, so this, what I have on the board, let me just put it. This is showing so if they say show the formation of the triglyceride, you will do everything that is on the board. If they ask you to draw the structure, if they ask you to draw the structure of a triglyceride, likely, you will only do this, all right? If they say show the formation, you must have a before and after. If they ask you to draw the structure of something, you just draw the after. All right? So that is triglyceride. Now, what is the difference between a triglyceride and the phospholipid in terms of this structure here?
One have a phosphate group. And it's
Right. So for your phospholipid, all you have to do is remove one of the fatty acid, all right, and put on your phosphate group. So you will have the oxygen. And again, so 2 things. You can put a P on it, but label it phosphate group. All right. So you can use representations, right? Now, if you want to be, as I said, specific, you have the oxygen, you have a phosphate with 4 oxygens. One of them is a double bond, all right? So this is where phospholipids are both of a hydrophilic, let me not say. The fatty, when you're doing the cell membrane, right? We use 2 H words to describe the head and the tail. How do we describe the head of the membrane or of the phospholipid? Which H word?
Hydrophilic.
Hydrophilic. And the tail is?
Hydrophobic.
Right. So the reason, if you do chemistry and you know about polar and, well, even if you don't do chemistry, you would have done this and know about polar and non-polar. So because the tail is made up of carbon and hydrogen, it is non-polar. So the tail, it is made up of carbon and hydrogen, so it is non-polar. Now, is water polar or non-polar?
Polar.
Polar.
Right. So we need to remember that water is polar. So let me just put some notes at the top. Create this. All right. So we know that water is polar. The phosphate group of the phospholipid is polar. The hydrocarbon, so hydrocarbon means it is made up of carbon and hydrogen. So the hydrocarbon tail is non-polar. The next important statement, polar mixes or interacts with polar. Polar and non-polar do not interact. Or if I want to say mix. Remember the same saying, like dissolves like, right? The reason why your phosphate head is hydrophilic is because it is polar and water is polar. So polar mixes with polar. So that is why the phosphate group is hydrophilic. It likes water. So when they say it likes water, it can interact with the water. And the hydrocarbon tail now, that is non-polar. Non-polar and polar, they do not mix. So that is why your hydrocarbon tail is hydrophobic. It is non-polar. So that takes care of the phospholipid. All right, moving along again. Anybody writing? I'm going to clear the board. All right. So, okay. All right, so this structure on the board, it is which polymer, which polysaccharide?
Sucrose.
Remember
Cellulose.
sucrose is disaccharide. All right,
Cellulose.
so for the persons, one of you that said cellulose, tell us why how you know it is cellulose?
Yeah,
Because-
because the glucose them turn upside and down when them are born. So
Ah,
one
right.
turn up, then down, then up again.
Yeah. No, you see, if they ask you for like a little description about cellulose, where you say it turns upside down, we say the glucose molecules rotate
Oh,
180, right? So the glucose molecules rotate 180 degrees. So as I said, it flipped. But in terms of if they ask you it on the exam, you would say it rotates 180 degrees. Right. So as I said, this one is pointing up, the next one in line, it flips downwards. So that's 180. And then the next one, it flips up again. So as I said, it alternates up and down. So once you see it goes up, you don't even have to start up. You start it down and the next one goes up. Once you see it alternates 180 or by flipping up and down, that is how you know it is cellulose. And you don't need more than 3 to show that. All right. So if they ask you to draw a portion of cellulose, use at least 3 glucose. That you can see that it goes down and up. Right? So that is the key feature that you look at to identify cellulose. The molecule flipping up and down each time, one after the next. Jason. All right. And someone texted it, right? It is 1,4. Don't just say 1,4. Is it what should come in front of the 1,4?
Beta.
beta.
Right. So the type of bond, just John arrow. So it is beta. And why we say beta 1,4?
Because it's formed from beta glucose.
That is correct. So the monomer, so the bond is 1,4 glycosidic bond. What would be the monomer?
Beta glucose.
Beta glucose, right? Now, what is the main function of cellulose?
Structure.
Where is,
One for
please,
the
sir,
cell.
yeah,
structure?
continue. No, sorry, what is the main function of cellulose?
They give structure to the cell wall of the plant.
Plants.
Right, right. As you know, cellulose is in the cell wall of the plants, and you are correct. Give structural support. Let's put that on the board. So the most important function here, it gives structural support. Right, so that's so, to identify it, the type of bond, you can tell a function, a little description, the monomer. All right. So let's do this again with the next polymer. All right. I'm going to clear the
Wait,
book.
sir, give me a minute.
All right. Question, what is while you're writing, what is the name of the reaction in which you can get back the monomer from the polymer?
Hydrolysis.
Right.
Hydrolysis.
Yes. So if you want to get back glucose from cellulose, it's called hydrolysis. They have condensation and they have hydrolysis, right? Give me an example of a next polysaccharide and the type of bond.
Starch.
Starch.
You have one.
Starch,
You have 1,4 glycosidic and 1,6.
right? Which 2 polymers make up starch?
Alpha and beta.
Aminopectin. Oh,
Oh, wait.
Yeah,
amylose and
amylopectin, right?
And,
That is correct.
amylose and amylopectin.
Shashanika, you finished?
Yes, sir. Yes, sir.
All right. Oh, conjugates. All right, so we're doing starch. And it says starch is made of amylose, and amylopectin. What is, so amylose and amylopectin, both of them are also polysaccharides. What type of bond exists in amylose?
1,4-glycosidic.
Right.
Beta
And
one.
they are made of alpha glucose, right? So both of them are alpha 1,4. But starch,
Never mind, sir.
so starch, however, is bond 6. So when you're connecting amylose to amylopectin, that is where the 1,6 comes into play. So I'm going to do that quickly. You can see it again.
Wait, sir, for amylopectin and it includes, so it's of the 1,6 branches on it.
I'm
Or
not
just-
sure. I just
Okay.
put the 1,6 out here, so for starch. Right. So in starch, this is why it have both 1,4 and 1,6 when you're connecting the amylose and amylopectin. All right, so let us draw glucose. Yeah. When you're doing these types of joints for the polymers, you don't need to fill in all the H's and OH. Right? So as we know, this carbon here is carbon 1, 2, 3, 4, 5, 6. This carbon here, 1, 2, 3, 4, 5, 6. You can see that we have the 1,4 glycosidic bonds. This is carbon 1. All right, it should match in line. All right.
Sir,
Yeah,
doesn't the amylopectin also have 1 to 6 bonds?
no, the branch between, it's the branch between the amylose and the amylopectin where you get the 1,6. Like, let me show you here. So this is carbon 6. It will have the OH group, right? CH2OH. And remember this carbon 1, it has an OH group, right? So you're removing the OH and H. So this is carbon 6, this is carbon 1. And that is how you get the 1,6. Let me just draw a line here for the oxygen. All right. So you have amylose, and you have amylopectin. But because of the branching now, that is where the 1,6 comes into play. All right. So in starch, you have 1,4 and 1,6. All right. So on the exam, if you get any of these joints, once you see branches, or once you see glucose joint at the top and some below, and you have this connection, it is either starch or glycogen. Based on the info provided, you will know whether it's starch or glycogen. Right? Because glycogen is similar to starch. It will have 1,4 and 1,6. So once there's a branch, you will have the 1,6 coming into play.
But sir, glycogen is more branch than amylopectin. So eventually with the amount of branches, you will know that it's not amylopectin, but it's glycogen.
Got to. And they don't really give you a lot of, like, if they give it an exam, you won't get a lot of glucose, just like 3 of 3 below. But yeah, they can use that info as well. All right, so good job on that. By the way, which enzyme would break down this molecule?
HCl.
No, enzyme,
Amylase.
right? And it will be broken down into what?
Glucose.
No,
Oh, amylose. Wait, Sarah, which one?
one M word.
What M word?
Yeah, M,
Maltose.
Maltose.
right? Yeah, maltose. And then maltase would break it down into glucose. Maltase.
Can you
With
repeat that because I'm not catch that.
amylose, sorry, starch is broken down into maltose, right? By amylase. And then maltase breaks down maltose into glucose. So with the enzymes, when it comes to the sugar and the enzymes, the sugar ending OSE and the enzyme ending ASE. So like sucrose, all right, so lactose, the enzyme is lactase. Maltose, maltase. Sucrose, sucrase. Right, so the enzymes, when it comes to the sugar and the enzyme, is just the O and the A. Right, so remember, amylose and amylopectin, they are polymers, So it's not like they're not breaking down starch into amylose, because remember, starch is amylose itself and amylopectin giant. If you're breaking up starch, you have to break it down into something simpler. Amylose is not simple. It is still a polysaccharide. All right. So you break it down into maltose, which is a disaccharide. And then the maltase will break it down into glucose, which is your monosaccharide. All right. So what is the main function of starch?
Is it the plant them store food as cause it not really reactive, so them get for like,
So it's an energy store, right?
Yeah.
Just like glycogen. So that is why they say glycogen is animal starch. But they act as energy reserve. So starch is for plants, glycogen is for animals. So the two of them have similar roles, which is as an, if you want to say energy reserve or energy store, right? Right, I'm going to clear the board. Good. All right, let's go again. All right, so that is sucrose. Add water to sucrose. What are we doing to the sucrose?
We are
Yeah,
breaking
hydrolyze it.
Right. So the name of the reaction occurring is
hydrolysis.
Hydrolysis.
right. Now sucrose. Is it a monosaccharide, disaccharide, polysaccharide? What is it?
I think it's a polysaccharide.
Disaccharide.
Disaccharide.
All right. Because as you see here, X and Y. Right. So we break it down into X and Y. Before I forget, what type of sugar is sucrose?
Non-reducing sugar.
Reducing sugar is correct. All right. So what should X and Y be in terms of name? What is X and Y?
Glucose and fructose.
Right.
Wait, alpha glucose and
Beta
beta
fructose.
fructose. Oh,
Yes. All right. So all you need to do is draw glucose and fructose. All right. Do that quickly. H2 OH. Alpha glucose and beta. Right. Yeah, correct. Referring to the persons in the comment section. Is this correct for alpha glucose?
no,
Tell me what is wrong.
the OH must be at the bottom. Like it for the below the something for the first carbon.
So, so OH, it should point downwards. All right. Then OH. That's it for glucose here. No, there's a H in here. Fructose is the one that has the 5-sided. All right. So oxygen in the middle. This goes here. This goes here. This goes here. This goes there. All right, so this is carbon 1, carbon 2, carbon 3 is here. This is carbon 5, does not have an OH group. Here, we have CH2, OH. So with the fructose, it kind of shaped like a pentagon, a 5-sided ring. And the CH2 OH groups, we have 2 of them, one at this side and one at this end. All right. So we have to move on again. Okay, no joins. Wait, what is this diagram representing?
Phospholipid.
Phospholipid.
All right. And if I was to label it, what would be these two, this area?
The fatty acid tail.
All right. So two fatty tail, and this structure here.
Phosphated.
Right. What if I told you to label it as hydrophobic and hydrophilic? Which part
Is
would be hydro?
hydrophobic and the head is hydrophilic.
So this portion, it would be hydrophobic, and here would be hydrophilic, correct? All right, so let's get in. Anybody writing? Because I'm erasing.
Yes, sir.
All right, let me. All right, let me know when you finish. All right, in terms of the fluid mosaic model, what are some components of it? Before you answer, the person that is writing, let me know when you finish. All right, go ahead now. What are some components of the fluid mosaic model?
Yeah, the cholesterol.
We have cholesterol. What else should be there?
Glycoprotein,
Right, that is correct as well. What else?
Phospholipid bilayer.
Right, that. Mm-hmm.
All right, sir, I'm finished.
All right, what else?
The channels,
Is it Pete?
the channels or the carriers.
Right, channel protein and carrier protein, right?
Glycolipid.
The integral protein.
The carrier and the channel protein, they are integral, right?
Oh,
yeah,
them these are fair protein.
Right. No, nobody never said that as it. Right.
Transmembrane protein, sir.
The
Is that
transmembrane is the same as integral. So transmembrane, they span the entire membrane.
Sir, cholesterol.
Right. They said cholesterol. All right. So let's
so you
just.
have the inner and outer parts, right?
I think I said inner and outer, as in. You mean the the part facing the
that part.
cytoplasm? Right. Oh, all right.
I have glycolipid.
Right. No, on the exam, you don't need to waste time and try to draw any fancy 3D stuff, you know. Alright. Just this is good enough. Alright. So as we know, the lipid bilayer arrange itself with the head facing the water, right? And the tail away from it. Right, at this point, I can put in, let's put in a channel protein. So you can put in whatever you want. All right.
So the overall diagram is called the phospholipid bilayer.
Right.
Okay.
And if you're asked about the fluid mosaic model, it's the same thing we're drawing. All right. So you put in, so these are this in red, you have the lipid bilayer. This one here is the channel protein. So in blue, channel protein. So this part is the channel. So things can just pass through easily. All right, so that is what it's called, a channel. Just move this. So we have the channel protein. Let's just put in some more bilayer. By the way, when you're journey, just take a time to ensure that the heads are close to each other, right? And we can put in now, we have the channel protein, we can put in the carrier protein. Look, something like this, because with the carrier protein, it will actually, things should be able to bind to the inside of it. So just make it like a V shape, right? Don't have to be anything really specific to it. Just make it of a V shape so something can actually bind.
So whatever is passing through it adjusts to the shape.
No, we don't really say that. It's not like with enzyme where it's it have to bind to like active site and so forth. In terms of explanation, when we do facilitated diffusion, right, after this, we just mentioned that the particle, like let's say glucose, it will bind to it, and that will cause it to change its configuration. It will flip over. But as soon as I draw this, we will go into that part of the explanation. All right. So what do we have so far? This here is the what? The channel protein. This one is the, did I say it was again? Carrier protein. Just write it. What else do I need to put in the on this drawing? That is within the membrane.
The cholesterol.
All right. Let us draw some more. As you can see, all you're doing is just drawing like some stick person and putting things.
So isn't the peripheral protein
in
within the
between.
membrane?
No, on the surface.
Oh,
Yeah. They are the extrinsic. All right. So you say cholesterol. All right. You can just draw a little, like something like this. All right. Let's continue. All right, let's put on a peripheral protein at the surface. So these span the entire membrane, what these are on the surface. All right, what else is missing now?
The glycolipid.
All right. And that is on the surface, just something sticking off, right? All right, so let's just, all right, let us structure like that. Call this our glycolipid. Oh, this is our our extrinsic protein on the surface. So glycolipid and glyco, what else? Next, glyco word.
Glycoprotein.
Glycoprotein.
Right. Give me a second. Just put it out here. So they're kind of similar. They just sticking off the surface of the membrane. Did we leave off anything? Let's just label this as the lipid by layer. Down in this area, it would be the cytoplasm, or the inside of the cell. Right, if you want to put interior and exterior. So did I leave off anything? So see glycoprotein, glycolipid, cholesterol. Let me label it. Cholesterol. All right, so you should label this, be able to tell the functions. You can just sort the function from the study guide. All right, from this membrane, what we're going to focus on now is the channel protein and the carrier protein. So remember now, we know that the membrane from grade 9, grade 10 coming up, you learn that the cell membrane is semi-permeable, right? So certain things can pass through, certain things will not. All right, so certain things that are extremely small, so like your oxygen and your CO2, they can easily pass through. Put it in green. So your gases, it does not need any support, right? It can make its way through the lipid by, means that it can just easily diffuse and makes its way into the cell, right? Now, however, not everything can do that. When we're looking at the movement of particles across the cell membrane, the movement of particles, what term do we use to describe the movement of particles from high to low?
Semi-permeable.
No, listen to your question. What word are used to describe the movement of particles from high to low?
Diffusion.
Diffusion.
Right. Now, at this stage, we become very specific about the type of diffusion, right? What are the two types of diffusion?
Simple and facilitated.
Simple and facilitated. Now, as the term suggests, facilitated, what does facilitated mean in general terms? Outside of this science, if you hear facilitate, what does facilitate mean? It means to help, right? To assist, all right, or to allow something to happen. Facilitate, which means that one of these proteins, either the channel or the carrier, will facilitate a certain protein. So as I said, when it comes to diffusion, so we're looking at movement of substances across the cell membrane, right? And that is done by diffusion. Now, diffusion is of two types. One is simple, and two is facilitated. Now, apart from diffusion, there is a next word that describes movement of particles, but this time it's from low to high. What word is that? Our phrase.
Active transport.
Active transport.
Right, active transport is correct. So when it comes to movement of substances across the cell membrane, we use diffusion. That's the first one. I'm going to put the other down here. We use active transport. Now remember, when it comes to diffusion, some of the particles are not small enough to pass through the membrane. So they will use the channel protein. They will use the channel protein and the carrier protein to assist with the movement. Now, outside of that, there are bigger molecules that cannot make it through the channel protein or the carrier. So they are too big for the protein as well. Anybody know the movement in that scenario? So molecules that are too big for just passing through the lipid bilayer, they use the channel protein or the carrier protein. But there are some that are too big for the channel protein and the carrier protein. So they have to use a next means of transport. Do you know any other means by which things get transported across the membrane? An E word, two E word.
Oh, endocytosis
Endocytosis and
the next one.
Phagocytosis.
And
Exocytosis.
right.
Exocytosis, yeah.
They call it mass flow. Under this, it is endo. Endo means what? Going in or out of the cell. Endo.
in
All right. We have endocytosis and exocytosis. All right. So we're going to look at these quickly. When it comes to simple diffusion, it is the channel protein. So for simple diffusion, it is channel protein. So we can just highlight that from here. And the facilitated diffusion now, that will be done by the carrier protein. Active transport is also done by the carrier protein. And as I said, with the endo and exocytosis, it does not involve the proteins. All right. We're going to look now how the carrier protein works. We don't need to look at the channel protein. Reason being, the molecules, they will just flow through the channel. As the name suggests, it is a channel. So just imagine the molecules just sliding through the channel. All right. Remember, diffusion is from high to low. So the molecules will be high on the outside, and they simply just diffuse into the inside of the cell where it is low. So the molecules are moving from high to low through the channel. All right. So in simple diffusion with the channel protein, no energy, no assistance is needed. They just slide through. All right. Carrier protein that we need to look at. Right, so before I clear the board, anybody writing? All right, so let's continue. Just a second. Give me a second. All right, let me just. All right, so this right here is going to represent the cell membrane. And the carrier protein, I'm going to put it here. So remember, it has a little, like a V shape. So it's diffusions. All right, hold on. This is the inside of the cell. And this is the outside. So remember now, molecules need to get inside. So it is going to be high on the outside. So the first thing is that the molecules, not all of them, one of them will enter the channel protein. All right, so first, one of the molecules is going to enter. So I'm going to draw it again with the molecule inside of it. Now, once the molecules enter, it will cause the protein to change its configuration. So the protein is actually going to turn around or flip. Just draw this a little further down. So in this step, the particle binds to the protein. Particle, it could be glucose. All right. So for example, we're looking at the diffusion of glucose. Glucose will bind to the protein. Let's be specific on the exam. It binds to the carrier protein. Once it binds to the carrier protein, it is going to cause the protein to now turn around to the inside of the and face the inside of the cell. Okay. The particles bind to the carrier protein. So the glucose enters and binds. Once it binds, notice the protein, it now turns around and it is going to release the glucose. When you join it, this line here, you would just erase it. And so the glucose is now released. So once the glucose is released, the protein reverts or returns to its original shape. If I want to put configuration. So once it releases it, you would draw up this diagram below it. It will now turn back and face the outside of the cell. So next molecule of glucose can go in. All right, so this is how facilitated diffusion works. Molecule binds to the protein, it turns around, releases it. Once it releases it, it turns back around and pick up a next one. All right, and so it continues. There was a question, I don't remember which year. I'll probably look for it for tomorrow. But you have two forms of, let me just do it. So you had a graph, right? One with a straight line. And then I think it started straight, but then it became constant. I think it was asking which line represented facilitated diffusion and which one was simple diffusion. So like on the y-axis, you had rate, and then what is concentration? As concentration, yes, it was concentration. As the concentration increased, the rate of diffusion was increasing. Notice for this one, even when the concentration of the, let's say substrate, well, enzyme is sulfate for enzymes. Let's say when the amount of particles increase after a while, the rate of diffusion for this curve, it became constant. So my question, which of these lines do you think is simple, diffusion, and which one is facilitated?
Thermophile say the straight one are simple,
Mhm.
and the one where increase over time and then remains constant, then
Yeah.
gets constant is facilitated.
Tell me why you think that.
Yeah, before my
You are correct, by the way. So just take a minute and tell me why you said that. Just remember what was done in simple diffusion versus facilitated.
because in a simple diffusion, as the number of particles increases from the higher, wait, sir.
Yeah, man, no problem. Can't
It
take it.
increases as it goes through the channel path to the
All right. And what would be happening for the carrier? What would cause it to not increase any further? Even though you're increasing the concentration, the rate just get constant.
how the particles become smaller. I don't know.
All right. So if you look on the board, right? Let's say you have one channel protein. And you have, all right, let's say you have two channel protein and you have 10 glucose molecules. It's just two channel protein that you have, right?
Yeah.
Right. So, just a second. Let me put something on the board.
So, sir, question, because in a simple diffusion, the particles them move itself, them can move at different rate. But because in a facilitated diffusion and the carrier protein and a eat one, so it's a go at its own rate, so it never really change rate every minute. So it a become steady at one point.
Right. And then it's steady at one point, meaning, like, let's say it's two, right? When the two of them have in a glucose molecule, the others will just have to stay out and wait, right?
Yes,
So,
sir. To the
yes.
process.
Right. So let's look back at the channel one. So with the channel, it doesn't matter how much glucose is on the outside, right? They can just simply flow through the channel, right? Because it's not like the channel protein is taking it up, The channel is what, as it says, is a channel. So they're just simply passing through. So when they increase it, they move faster and faster. But with the channel, the carrier one now, it is the proteins that are actually binding to them and then releasing it, which means that just like similar to an enzyme, right? Once it gets constant, it means that the protein is slowing up the process, right? So if the concentration is increasing, as you can see here, right? But the rate of the diffusion is not increasing. It means that the problem is not with the concentration of the particles. The problem would be with the proteins, because it is the proteins that are transferring them from the outside to the inside. So it means that when you increase the concentration, the rate will increase up to a point. Then you have a finite amount of proteins to do the transporting. It is the proteins that at this point now, we can say all of them are occupied with molecule. So it doesn't matter how much more you put, it's like them just have to wait. So just imagine you are going into, like, let's say a bank or a taxi. If a taxi hold five people go in and they, no matter how much more leave out, them just have to wait. Understand? Not sure. Yes or no?
So, sir, the protein them are basically a work on the carrier. The glucose basically work on the carrier protein time. So no matter how much they're there, if a 5 the protein can carry, and that's it a go carry at a
Exactly.
constant.
Right. So once you get you see entire door graph, and it gets constant, something is affecting the process, right? So this one is clear. Once concentration increase, rate increase. But with this one, something is influencing why the rate cannot increase any further. And it is because it is the protein that are actually taking up the glucose and transporting it. The protein is slowing up the process. And the channel one, they are literally just passing through. Nothing is carrying them. So they are just sliding, going across the membrane. Their rate can just increase infinite. And this one.
So it's because the protein is slowing the process. That is why the concentration becomes constant over time, because
Wait, no, it's not the concentration get constant at the rate.
the rate gets constant over time, because not all particles can pass through the carrier channel at once.
Right. Yeah, it has a weight. Yeah. So because of the protein are transported, if all of the proteins occupied at a particular time, then the rest of glucose molecules that needs to be transported, yeah, it has a weight. So the rate just gets constant. All right, yeah, so that was that. I looked for the paper correct still and shown. All right, so that was for, let me scroll down. Yeah, facilitated diffusion. With active transport, it will be the same thing with a minor adjustment. All right, what did we say with active transport? It is moving from where? High to low or low to high?
Low to high.
Low to high, so you can, yeah.
All right, so the only thing we're going to adjust is the amount on the outside. So let's put about 3 on the outside and then a lot on the inside. Something else, what is needed for active transport apart from the carrier?
ATP.
Right. Just think about it. If you're pushing something up a hill versus down a hill, if you're pushing something down a hill, do you need to use energy?
No, sir. It
Right.
does flow free.
Right. But if you're going up a hill,
You
right?
need energy.
Right. So going up the hill is like, in this one, we would say it is going against its concentration gradient. When we're moving something, all right. So movement from low to high, we say particles are going against their concentration gradient. All right, so from low to high, they are going against their concentration gradient, so energy is needed. So the only adjustment to this, you put fewer molecules on this side and more on the inside. And you are going to attach ATP. So the glucose will bind and so will ATP. All right. And the releasing of it, once it is released, your ATP will be converted to ADP. All right. So when you're using ATP for energy, ATP is converted to ADP. So you go from triphosphate to diphosphate. All right. So that is our energy. When we say energy is used up, or we get energy from ATP, in this process, ATP is converted to ADP. ATP is binds to the protein, and in the process, it will be converted to ADP. Right? So the same mechanism, just that this one, you will need ATP, and you put fewer molecules where you're moving it from. They're showing from out to in, few on the outside and more on the inside to show that you are moving it from low to high. All right. All right, let's clear and move again. We're going to look at the endosymbiont theory. Is anybody writing? All right, good. So let me just erase the name. So the adjustment that I just made is for active transport. With active transport, ATP is needed. So this was the adjustment for active transport. All right, so what are the two, let's say, the two main or say two categories of cells? I'm not sure if I wanted to phrase it right. All right, yeah. What are the two cell types? The two major cell types? Not in terms of
Prokaryotes and
all right.
eukaryotes.
Okay. Yes, it will be saved to the channel once it ends. All right, so endosymbiont theory. So we have two cell types. So we have prokaryotic cells and eukaryotic cells. Which of these two cells came first? Is it the prokaryotic cell or the eukaryotic cell?
Prokaryotic.
All right. We have the two cell types, and we said prokaryotes existed before eukaryotes. Tell me a main feature of the prokaryotic cell. Or just tell me something about prokaryotic cell.
It doesn't have membrane enclosed organelles.
All right, does not have any membrane bound organelles. Does the eukaryotic cells have that?
Yes.
All right, so said that the prokaryotes existed before the eukaryotic cells, and that eukaryotic cells have membrane bound organelles, while prokaryotes don't. Prokaryotic. So prokaryotes existed before eukaryotes, and eukaryotes have membrane-bound organelles, while prokaryotes don't. This is where now the theory is coming into play. They are suggesting now that prokaryotes evolved into eukaryotes, right? Which means that somewhere along the line, the prokaryotic cells obtain organelles. So a theory which is going to show how prokaryotic cells became eukaryotic cells. How did they do that? Or this suggestion? Before I put forward this suggestion,
entered the bodies.
I'm going to put forward some clues as to why they said that. Hold on. So the theory, this theory explains how prokaryotic cells evolved into eukaryotic cells. The main, what should I say, the main clue or I know I'm going to use clue, but I will switch it out of the main clue, evidence. Yeah. The main evidence All right, so let's just run back over what we have so far. So what this theory is trying to do is show how prokaryotes evolved into eukaryotes. Eukaryotes have membrane-bound organelles such as mitochondria and the chloroplast. Prokaryotes do not have it. And then we said that the evidence for this theory came from observing the mitochondria and the chloroplast. So what that means is that the mitochondria and the chloroplast have things in common to the prokaryotic cells. There are similarities with all right, I will give you a chance to write and then I clear the screen. All right, just checking, is anybody writing? All right, so let me just clear this. So what they're saying, if the mitochondria and the chloroplast shared similarities, certain similarities with the prokaryotes, maybe they were actually prokaryotes. All right. So this is what they suggested happen. So this cell right here, we're going to call it the ancestral prokaryotic. Remember, at this point, we don't have any eukaryotic cell as yet. This is the ancestral prokaryotic host cell. We're going to call it host cell. All right. It will have in its DNA, of course. Right. Now, you have a smaller, so how the theory works is that the prokaryotes are of different size, right? You have some larger ones and you have smaller ones. So the larger ones can engulf the smaller one. So I'm going to draw a smaller one on the board. And so one looking like this, right? Now, some of them, the theory, some prokaryotic cells have the ability to carry out aerobic respiration. All right. If this was an organelle, which organelle would it represent based on how it looks? Which organelle do you think it would represent?
Mitochondria.
Right. So, what is the function of the mitochondria, by the way?
To produce ATP.
Right. So, produce energy. Yeah.
Yeah.
Right. So, carry out respiration, right? In essence, or in general terms. So, this is your aerobic prokaryotic cell. So remember, at this point in time, no membrane-bound organelles. So you have a host cell and you have a smaller prokaryotic cell that is able to carry out aerobic respiration. What is going to happen is that this cell will engulf this bacteria. Yeah. All right, so you have this reacting, you get this, right? It is engulfing it. And then now you have it inside of it. So this ancestral prokaryotic cell now, after say, hundreds of years, just evolution, right? Not evolution as yet, wait. This engulf it, right? And then after several years of evolution, more than several years, it becomes our eukaryotic cell. All right? Now, this was a prokaryotic cell, right? But after evolution, it evolved into becoming the mitochondria. Right? It is no longer a prokaryotic cell. It still has the capability, as you know, to do what? Carry out respiration. Mitochondria. So it was a cell by itself with the ability to carry out aerobic respiration. It was engulfed by a larger ancestral prokaryotic cell, clearly without the ability, right? Engulf it, the organism, the prokaryotic cell, it did not, let's say the prokaryote did not destroy it. So the host cell, it did not destroy it. It was still there until it evolved into the membrane-bound organelle that is the mitochondria. All right. So this eukaryotic cell cannot carry. So eukaryotic cells, we have plants and animals, right? So this does not have any chloroplast. So it will be the heterotrophic. Hetero. Once I'm done explaining, if you're not sure about something, you can ask.
So you can start back from the engulf part when you finish.
All right, so yeah, I'm going to do it for the plants now. So eukaryotic cells, they have mitochondria. Prokaryotic cells do not have any mitochondria. The theory is showing you how the eukaryotic cell ended up with the mitochondria. Remember now, they are suggesting that the mitochondria was an actual prokaryotic cell. They need to get that part. The mitochondria was actually a prokaryotic cell, and it was engulfed by a larger prokaryotic cell. This, all right, so just technically, let us say this was the mitochondria, right? That engulfed into a larger prokaryotic cell. Now it becomes an organelle. After several years of evolution, it becomes an organelle, right? So this is a prokaryote, no organelle. Now you end up with a eukaryotic cell with membrane-bound organelle. All right, so that is what this theory is basically suggesting. How you go from an organism with no organelles to one with organelles. All right, and the two key organelles we use is the mitochondria and the chloroplast, because they have things in common to prokaryotic cells. And I'm going to list it shortly after this. So you have an aerobic, you have a prokaryotic cell capable of carrying out cellular respiration. You had the next one now. There's two of them, you know. So one capable of carrying out aerobic respiration. You have a next one capable of carrying out photosynthesis. We call it the cyanobacteria. All right. You don't have to, if you don't remember it, that's fine. Just remember, if they ask about it, one of them have the ability, so I'm going to put prokaryotic cell with the ability to carry out photosynthesis. Prokaryotic cell with ability to carry out photosynthesis. Which organelle do you know that is responsible for photosynthesis?
Plants.
No, which organelle?
Chloroplast.
Right. Yeah. So what do you think, based on what I did for the mitochondria, what do you think is going to happen to this prokaryotic cell?
It's going to engulf something will look like a chloroplast.
Right, so this same ancestral prokaryotic cell, right? It can engulf. All right, so let's show the engulfing portion of it. All right, so it is going to engulf the bacteria. It's not yet a chloroplast, right? Still bacteria. All right, so now this prokaryotic cell with ability to carry out photosynthesis is now completely engulfed. Right? So this is the one that will become if the one with mitochondria is heterotroph, which one, what do you think, the one with the chloroplast, will it be heterotroph or autotroph? Once it has chloroplast, it will be able to do what?
It will be an autotroph that can make its own food.
Right. No. Give me a difference between plant cell and animal cell. A key difference. if you remember.
One have chloroplast and one don't have chloroplast.
Right. But the plant cell, it has mitochondria as well, right?
Yes, sir.
Right. So this autotroph are from up here, this one with the mitochondria, it can engulf one with the, it could engulf the chloroplast. So let's just show this one engulfing the chloroplast. All right. Or I could just put the chloroplast in from over here. I mean the mitochondria. So what happens? Some of these ancestral prokaryotic host cell, some would have just engulfed the mitochondria and stay as an heterotroph. But some of them engulfed both the mitochondria and the chloroplast. So inside of it, you will have both mitochondria and the chloroplast. Because as you know, plants have both mitochondria and chloroplast. So let us see if we can just quickly summarize this theory. The theory is trying to explain how we end up with eukaryotic cells, basically a cell with membrane-bound organelles. The two organelles of importance is the mitochondria and the chloroplast. The reason they're of importance is because they share similarities to prokaryotic cells. Good? Now, how does it start out? It starts out with a small aerobic, small prokaryotic cell capable of carrying out respiration. And they have a next one capable of carrying out photosynthesis. Now, both of these, right, will be engulfed by the bigger prokaryotic cell, right? Both can be engulfed by one of them in the case of this example down here. And in the example above, only the mitochondria is engulfed, right? And once it engulfs it, you just say over time, it evolved to where it just becomes an organelle, not an organism again, right? So in this one you have the mitochondria, and in this one you have the chloroplast and the mitochondria. One,
So
yeah, go
after
ahead.
it engulf the aerobic prokaryotic cell, it will engulf the bacteria.
Sorry, repeat that for me.
Sir, because I see you put the mitochondria in the one at the below, may I ask if
Down here?
yeah, if it engulf the cyanobacteria after it did engulf the aerobic prokaryotic cell. So if it's a
Right.
continue engulf more something.
Yeah, so so don't think of it as, even though on the board I just draw one circle, think of it as, let's say 100 of these, right? So let's say out of the 100 of them, 30 of them engulf a chloroplast as well. And the other 70 just stay as the heterotroph. Is that what I was asking? Just to check.
Yes, sir.
All right. And that same thing, right? Like they can ask, like, based on this, which one do you think came first, the heterotroph or the autotroph?
The heterotroph.
Tell me why.
Sir, because at the heterotroph, it did just have it engulfed the aerobic prokaryotic cell and it did just have mitochondria in there.
Right.
Then the autotroph, it did originally have a mitochondria in there and it would engulf the cyanobacteria, so it have a chloroplast.
Right. So in this theory, right, this is one of it as well. If you think the heterotroph was first before the autotroph. So this was one way of viewing it. But again, all of this is theory. All right. So this is the theory. If they ask you to explain it, you can draw your diagram and do the explanation. You can just take a screenshot of the board if you need to, because I'm going to jot down now the similarities between, not the similarities, the evidence. So this portion of it is explaining the endosymbiont theory. They don't have to ask for the explanation. Sometimes they just ask for the evidence. So what I just did was the explanation. I am going to put the evidence now on the board. All right, I'm going to clear the board. All right, so remember now, as we said, the key thing that we used was with the mitochondria and the chloroplast, and that they share certain characteristics with the prokaryotes. So it's the characteristics between prokaryotes and eukaryotes that we actually use to tell or to propose this, this theory. So what are these similarities? Mitochondria and chloroplast has their own DNA. Remember, we normally say the nucleus contains the DNA, right? Mitochondria and chloroplast has their own DNA. They have the same size ribosome, which is the 70S ribosome. Let's see if I left out any important one. Whenever I put they, I am referring to mitochondria and chloroplast. On the exam, do not use they, just be specific.
Sir, and also the organelles generally have similar sizes to prokaryotes.
Right, not just the ribosome here. So,
And they have their own DNA too, sir. Sir,
Yes.
they have their own DNA too. So just like how you don't have any membrane bounded linear DNA in prokaryotes, you have that
Oh,
in
yeah. In terms of the
the
shape. Yeah.
organelles.
Thanks. Yeah, look for that. In terms of the shape. Thanks. All right, so that should be enough for us. All right, so all of this evidence is what suggests that prokaryotes evolved into eukaryotes, or that eukaryotes came from prokaryotes. Not the eukaryotes, the membrane-bound organelles were actually prokaryotes. This is actually showing organelles coming from actual organism. I shouldn't say come from, evolved. All right, let's run through enzyme quickly and then we break. Let me see. So when are we going to the other? Just let's have a break. Break now? Yeah. Or in the next 15 minutes. What do you want to do?
Sir, just finish module 1 and then we just do module
All
2.
right. Let's just use the next 15 minutes and run through enzymes. All right. Here are joins.
Okay, so that is everything on module 1.
No, there's little another proteins
That
and
is all.
water. Protein
Oh.
and water, but water soft.
Yeah, water soft.
No, let me just point this out. There. Like with the cell membrane, when you label it, you study the functions. Even though never list out the functions, so the lipid bilayer, you study the function of each part. When you do like the phospholipids, study the uses. All right. So glucose, cellulose, triglycerides, all of them, they have uses, function. So you must know them. All right. Yes, so let's continue. So enzymes, we already know that they are biological catalysts. All right. And we know that catalyst, what does a catalyst do?
Speed up a chemical reaction.
Speed up the rate of a chemical reaction by creating
Right.
an alternative path, something like that.
Yeah,
And is unchanged at the end of the reaction.
that part, yeah, it is unchanged. All right. So quickly, how enzymes work. So we have two models, right, of how they work. Let me just write, how do enzymes work? How do enzymes work? So we have two models. What are the two models of how enzyme work?
The lock and key
The
hypothesis, the
induced
induced fit hypothesis.
Right. So we have the lock and key, and we have the induced fit. All right, we're just going to make some important jottings. All right, so in the lock and key, all right, one, we know that the lock represents what?
The enzyme.
All right, so the lock represents enzyme. Now, when you have a lock and you are going to put a key in the lock, what is on the lock? Where does the key go?
In our hole.
Right, so the key, right? So the keyhole would represent what?
The active site.
Active site.
Right. So the lock is the enzyme. The keyhole represents the active site. And we all know that the key represents
The substrate.
right. Key represents the substrate.
Substrate.
Right. So after you mention all of this in nice sentences, what does this now mean? So the key is the enzyme, the keyhole represents the active site, the key represents the substrate. Now, what other comparison are you going to mention? All right, let me help you out. So when you have a lock and a key, right? Can you use any key?
Sir, every lock have a particular key to open.
Right, yes.
So which means that every enzyme have a particular substrate that fits the active site.
That is correct. So after I make these three statements, you would say that each lock
has a complementary shape to fit the enzyme. The substrate.
So not the substrate as yet, the key.
Oh.
You mentioned the lock and key again, then you mentioned the enzyme and substrate. So each lock, are the keyhole of each lock is specific or particular key. Now, we already mentioned what everything means. So, in the same way, the active site is specific or particular substrate. And the last thing, enzyme and substrate binds. When they bind, what is formed?
Products.
No, before you get
Enzyme, substrate.
complex, right? Enzyme and substrate binds to form enzyme substrate complex. Right. Once you get the complex, that is it. The enzyme will then work on the compound. Right? So they ask you to explain the lock and key. Once you get to the enzyme substrate complex, you are good. So enzymes bind with substrate to form enzyme substrate complex. So all we are explaining is how we get the enzyme substrate complex. All right. What will we say for the induced fit?
The enzyme change shape slightly to fit the substrate more perfectly.
Right. So what is the first difference now between induced and lock and key?
So induced the enzyme change its shape to fit the subject, while in lock and key, it does not change its shape. So
All right.
if the substrate cannot fit into the enzyme, the active sites of the enzyme, no product will be formed for the lock and key method.
All right. Good. So in the induced fit, the substrate shape of the substrate is not a perfect, right? As the lock and key would suggest, the shape of the substrate is not a perfect fit for the active site. What does the enzyme do when it binds to the substrate?
It changes its shape.
All right, so the enzyme,
so it fit properly.
all right, so the enzyme changes
Its shape.
the active site to fit the
Substrate. Mhm.
all right, properly. Let me just put that. All right, so it says induce. So once they bind, there's some change in configuration to put it properly. So in essence, just to wrap, lock and key, the enzyme, the substrate as the perfect shape for the active site. That is the essence of the lock and key. While with the induced fit, the substrate does not have the perfect fit. When it binds, there's some adjustment that has to be made in the active site. All right, so that's that. Let's look at factors that affect enzyme. Before I continue, anybody writing? I'm going to clear the screen.
No, sir, can do this thing.
All right. So quickly again, what are the factors now?
Temperature, concentration,
Temperature,
PH
concentration.
and pH.
Be specific about the concentration. Which concentration?
One substrate.
Enzyme concentration and substrate concentration.
Substrate concentration, enzyme concentration. Factors that affect enzymes. All right, I'm going to put 4 graphs on the board. So each factor has a graph.
There's in the exam, if them ask you to explain how any of these factors affect, I can just draw the graph or I have to put my explanation.
No man, if they say explain, I have to explain.
Oh.
Yeah, I don't need, unless them say explain this, explain how they affect, explain using with the aid of a graph, explain. If they don't say with the aid, you don't have to draw it. Oh, well, I will have to label these two. All right, based on these two, all right, let me just label it. So this will be enzyme right, is this. All right, so this one is substrate concentration. This is enzyme concentration. This is temperature. And this is pH. All right, so temperature, the graph, it increases, right? And then decreases. For temperature, which point on the graph, if they're going to ask you for a point on the graph, which point are we interested in?
The optimum temperature, so the peak.
Right. So you just find the peak. Right. So that is the optimum temperature. If you want the maximum rate, you would go to the y-axis.
Yeah.
So the 40, that is the optimum temperature. And over here now, you would get the maximum rate. Now, in terms of explanation, right? I'm going to call it A. Over here is A, over here is B. For A, as temperature increase, kinetic energy increases. Kinetic energy increase. Once kinetic energy increase, collision increase. And if collision increase, rate increase. All right, so for this side of your temperature graph, the rate is increasing because as you increase temperature, kinetic energy increase. So molecules are moving faster, more collisions are occurring. That is why the rate increases. All right. Once you pass the optimum, it starts to decrease. The reason why it starts to decrease, so I'm explaining side B now. It starts to decrease because bonds starts to break, right? Bonds in the enzyme starts to break. Once you break the bond in the enzyme, it is going to start to lose its shape. The bonds break, enzyme lose shape. All right. If you continue to increase the temperature, eventually
to include about how it change structure, like the tertiary structure change.
repeat.
Like when you talk about after the
Yeah. Oh yeah. So in terms of enzyme lose shape, enzymes are proteins. So I'm just making the judgments here. If you want to expound and say the tertiary structure of the enzyme, it starts to unravel or break down. Yeah. So here, when I say enzyme loses shape, yes, it is the tertiary structure of the enzyme that is changing. It is falling apart in a sense.
and is that due to the amino acid bond breaking?
Don't say amino acid or the
Not amino acid, amino bond.
no, those bonds, all right, so bonds they have not the peptide bonds. So the bonds are like the hydrogen bonds, so intermolecular forces. Like the hydrogen
The
bonds,
peptide
yeah.
bond between the amino acids are breaking.
Right, yeah. So not the just to be clear for everybody, it's not the peptide bonds. It's the bonds that hold the tertiary structure together, like the hydrogen bonds. So you can put that the bonds, so just put that bonds that hold the tertiary structure together start to break, all right? So the bonds that hold the tertiary structure of the enzyme together start to break. So once it starts to break, the enzyme will start to lose its shape, right? Eventually, active site will completely lose its shape. And at this point it is denatured, completely denatured. Once it starts to that's because the enzyme starts to lose its shape. Right? Eventually, all the shape, it is completely out of shape. The substrate cannot bind any at all. Right? It is completely denatured. I can't remember everything. Just remember, when it's increasing, it's because temperature is increasing, collision is increasing. Right? And so the rate increase. Once it's decreasing, at least mention that bonds are breaking. Right? Bonds that hold it together, then break. And once it breaks, it loses its shape. All right, so at least remember that. For the pH, same thing again, except that we're going to start from in the middle. So we start from the optimum pH. All right, so take it from this point of view. To the left and to the right, it will decrease. So once you pass the optimum, the rate will decrease. The reason for that, unlike with temperature, right? Any adjustment in pH, bonds starts to break. All right, the hydrogen bonds start to break. So it change shape. All right. So above or below, above or below the optimum pH, hydrogen bonds break. All right. Again, once the bonds break, we know what will happen. The enzyme is going to change its shape. All right. So is this same thing like over here? That it is not the heat that is causing it to break. I'm just making some jottings here. Enzyme lose shape. There's a complete lecture on this in full detail on the channel. Just type in enzymes. And so I'm just making some jottings here. Enzyme lose shape, it becomes denatured. For these two graphs, the first part of the explanation is the same. In that, as concentration increases, the number of collisions between enzyme and substrate increases. Again, once you increase the collision, rate is going to increase. Concentration increases, the number of collisions between enzymes and substrate increases. If you want to be more, if you want to go a little more, you will say the number of, I don't have to mention it if I want to, I can go ahead. The number of enzyme substrate complex, number of enzyme substrate complexes formed per unit time increases. And so rate increases. All right, so for both of them in this one, as an increased substrate concentration, collision between enzyme and substrate is increasing. Same thing for the enzyme. Once you're increasing it, you get more enzyme substrate complex, rate increases. All right. Now, the only other part now is where it tapers off. Here, why it tapers off? At this point, the enzyme is completely saturated. All right. So at this horizontal line, enzyme is saturated. Saturated with substrate molecules. So all the enzymes present in the reaction, they are occupied with a substrate. Putting more substrate will not increase the rate. So we have the horizontal line, it means the rate is constant. And that is because the enzyme is saturated with substrate molecules. So a quick little side note. We have two enzymes, the two of them has a substrate. Adding more substrate will not increase the rate because the two enzymes are occupied. That is what happens here. Enzyme is saturated with substrate molecules. Increasing the concentration further will not change the rate. With this graph, enzyme graph, as I increase the enzyme concentration, the rate is going to increase. However, if the enzyme surpasses the substrate, same thing will happen again, right? You will not any further increase. So it's like, remember with the protein in the membrane, limiting the rate. So this is what happens. The substrate concentration, if I keep on increasing the substrate, the enzyme is going to limit the rate. So whenever you get a horizontal line, something is limiting the rate of the reaction. So with the enzyme graph, you have a finite amount of substrate. So if you keep on increasing the enzyme until it surpasses the amount of substrate present, then the rate is going to be constant. It is the same thing. It is the same thing that will generally happen. However, if you get a graph and you don't have this little curve on it, right? If you get this as your enzyme concentration graph, this will be your explanation. Don't mention anything about if you increase the enzyme above the substrate concentration. If it's a completely straight line, just explain that as concentration of the enzyme increase, collision is increasing between the enzyme and the substrate, the rate is going to increase. If they ask you to draw the graph, you draw a straight line, just like I did before. And you just put on this to mention what can happen. With the substrate one, do not do it like this. Go straight and then curve. The enzyme one, you can just add on this little portion. All right. So that is it for explaining the factors. Anybody writing?
Sir, what is the second point you have? What under the concentration explanation? The number of what? Wait, sir.
This- The number of enzyme substrate complexes
Yeah.
are
4.
formed per unit time.
Oh.
It cannot close. I just move. It's per yeah, unit time. All right, so that is it for the factors. The inhibition. What are the two types of inhibition that we have?
Competitive and non-competitive.
You're removing something.
And we have reversible and the irreversible. Right. Is anybody right? If you're writing, so just take a screenshot. I'm going to clear the screen now. I'll join. Inhibition. Competitive. And this is reversible. So in competitive, the inhibitor competes with the enzyme or the active site. Inhibitor and substrate has a similar shape. All right, so for example, if this is your enzyme, this is the substrate, this could be the inhibitor. So in competitive inhibition, because the inhibitor and the substrate have the same shape to fit the active site, the inhibitor can compete with this substrate. Why is it reversible? That reason.
Because if you increase substrate concentration, the substrate can be removed from the enzyme, or
Actually,
the effect can be reduced.
you can
And it's
improve
not
the rate.
permanent, it's temporary.
That of the explanation is how we can improve the rate, but it's reversible because the inhibitor, it don't stay there forever. It will actually come off after a point in time. But where say you increase the concentration of the substrate, you do that if you want to improve the rate of the reaction. Reversible, why it's reversible again? Right, it's reversible because the inhibitor will leave after a certain time. As I was saying, increasing the substrate concentration will increase the rate because the substrate has a greater chance of binding to the active site. Right? Let's speak on the non-competitive. I have to take a break now. So the non-competitive, it will not bind to the active site. It will bind somewhere else on the enzyme. It is called the allosteric site. All right, so I'm just going to speak on this. Allosteric. Okay. All right. So this is NC for non-competitive. The enzyme will bind to an allosteric site somewhere else on the enzyme. So for example, over here, all right? Let us say it binds over here. This is the allosteric site. In non-competitive inhibition, the substrate and the inhibitor has a different shape. The shape is not even of the importance here. It is that the inhibitor is binding somewhere else other than the active site. When it binds to that point, however, it changes the shape of the active site, and so the substrate cannot bind. I'm going to say it again. In non-competitive inhibition, the inhibitor binds somewhere else on the enzyme. That is called the allosteric site. When it binds, the enzyme changes the shape of its active site. Because the shape of the active site changes, the enzyme and the substrate cannot bind. So that is why it is non-competitive. They have different enzymes, inhibitor and substrate have different shape, so they are not competing. Right? Now, in this inhibition, increasing this substrate concentration will not help because the inhibitor and the substrate is not competing for the active site. So when they are competing for the active site, increasing the concentration of the substrate can help. But in non-competitive, it cannot help. All right. After up here and take a break. Okay.
So yeah, we're right to the explanation there.
Is it Pete?
We're right to the explanation there on the board or not?
Mega break. But this in the mega just send a link for the enzyme recording. There's about a one enzyme with everything in detail. It can just keep to it and write it off. But I'm gonna stop here so for now.
All right.
Okay. Before I stop it, is anybody writing anything at this point?
Yes, sir.
All right. Let me know when you're finished.
Thanks, sir.
Finished?
Finish.
All right. Let's see. What's the 7:30? Somewhere between 8:30 and 9. Yeah, I will. If I'm not starting 8:30, I will just check the comment. Just check the community section on the channel. If I'm not starting 8:30 and starting at 9, I'm just going to post it in the community section. All right. So at 8:30, you can just check. All right. So I'm going to close this meet.
Okay, sir.
All right.